In this video, we're going to try a second optimization problem. We've got a sheet of metal 30 feet long and 2 feet wide, and it's to be made into a trough by folding it lengthwise down its center. What angle theta will result in a trough of greatest volume? So theta is the angle between the two halves as we fold this. Alright, so I'm going to draw a picture viewed from the end. Viewed from the end, we just get this V shape. And since the length is a fixed value, we can maximize the volume by maximizing the area of this triangular region formed by the V. Alright, so those sides are each 1. Now, here's what I want to do. I'm going to cut this triangle in half. This is an isosceles triangle, so we can split it down the axis of symmetry, and those will be 2 right angles. What I want to do is I want to swing this one around, this half around here. It'll look like this. Alright, we'll swing it around. But then I want to fold it over this way. And when you combine it with this half, what we're going to get is a rectangle. So, what we need to know is this angle. Well, the angle theta is from here to here. This is actually only half of theta. How about we give that angle a new name? How about alpha? And we'll just have to remember that at the end, theta is 2 alpha. Alright, so what we want to do is maximize the area of this triangle, which is the same as the area of this rectangle. Alright, so that angle we're going to call alpha. Now, what we need is expressions for the, well, okay, we need expressions for these two sides. How about x for this side and y for that side? So now we need to somehow make an equation that relates the length of these sides of these 2 right triangles to the angle theta. Sounds like trig to me. So let's try this. What's the sine of theta? The sine of theta, sorry, not the sine of theta, sine of alpha. The sine of alpha is going to be the opposite side over the hypotenuse. Well, this hypotenuse is one of these sides, so that hypotenuse has length 1. So the hypotenuse has length x over 1, or just x. And what about the cosine of alpha? Well, that's the adjacent side, which has length y over the hypotenuse, so that's y over 1, or just y. And now what we need is to maximize the area. And that's x times y, or a equals sine alpha cosine alpha. See, we couldn't have left it as just x times y because that's 2 variables. We don't want the area to depend on 2 variables, right? Because this is our primary equation. How do I know it's the primary equation? Well, it says we want the greatest volume, so we want to maximize the volume. Well, we're actually going to maximize the area instead, but it's equivalent. So we want to maximize the area. That means this is the primary equation. This is the thing to be maximized. We need it expressed as a function of a single variable, so that's where these trig functions come in. Alright, it sounds like we're ready to differentiate. Alright, so A is sine alpha cosine alpha so that means A prime will be found using the product rule. So we will have sine alpha times the derivative of cosine is negative sine alpha plus the cosine of alpha times the derivative of the sine of alpha, which is the cosine of alpha. So that's the cosine squared of alpha minus the sine squared of alpha. Now to find the critical numbers. Is that derivative ever undefined? No, sine and cosine are always defined. Is it ever equal to 0? Could be. I think we need to talk about how big alpha can be and how small. First of all, let's go back to our angle theta. Remember how theta was defined? It was the area between it was the angle between the two sides of that trough. Well, it could be almost as small as 0. It can't be 0. So theta can be almost as small as 0 and almost as big as 180 degrees. Right, if it's 180 degrees, it's flat, but that gives us a volume of 0, so can't be quite 180 degrees. Alright, but now alpha is theta over 2, so let's divide everything by 2. And we get that alpha is between 90 degrees and 0 degrees. In other words, alpha is in the first quadrant. All the trig functions are positive in the first quadrant. Right, the first quadrant, all the trig functions are positive up there. How does that help us? Well, let's go back over to here. This is the same as, I put my squared in the wrong place. This is the same thing as saying cosine of alpha squared is equal to the sine of alpha squared. I'm doing two things. I'm rewriting it in different notation, and I'm pulling the sine squared term over to the other side, which means that cosine of alpha is equal to plus or minus the sine of alpha. But since we're in the first quadrant, that means that the sine and cosine have to have the same SIGN. They have to both be positive. So we're looking for values that make the cosine of alpha equal to sine of alpha. Well, how is that going to happen? Well, remember our rectangle. The cosine of alpha, that was y, and the sine of alpha, that was x. Right? We have that right up here. So we need x to be equal to y. Well, what does that tell us about a rectangle? It tells us that a rectangle is actually a square. So if this is a square, what angle is alpha? What's half of 90 degrees? Alpha is 45 degrees, which means that theta is 2 alpha, which is 90 degrees. So we've answered the question. It appears that our angle needs to be 90 degrees. The only thing that remains to be done is to demonstrate that we're actually getting a maximum. So how are we going to do that? Let's go back to A prime, which is cosine squared alpha minus sine squared alpha, or it's cosine alpha minus sine alpha times cosine of alpha plus sine of alpha. I use the difference of two squares factoring technique. I'm going to use the first derivative test. It turns out that I've already tried the second derivative test and it doesn't work. But let's use the first derivative test. So, we have one critical number, right? And that was 45 degrees. And we're only going between 0 and 90 degrees, so that means our two intervals are from 0 to 45 and from 45 to 0. So let's pick an angle. How about 30 degrees here and 60 degrees here? Those are our test numbers. Now what's sine alpha minus cosine alpha? And what's, oops, that's not right. I'm going to plug these in here. What's cosine alpha minus sine alpha? What sine is that? And what's cosine alpha plus the sine of alpha? Our A prime is actually this times this. Alright, so if we put in 30 degrees, cosine of alpha, cosine of 30 degrees is root 3 over 2. Sine of alpha is 1/2. I believe that's going to be positive. And actually I know this cosine alpha plus sine alpha is always going to be positive because sine alpha and cosine alpha are both positive. That's made up of two positive things. Now what about over here? 60 degrees, the cosine of 60 degrees is 1/2. The sine is root 3 over 2. That'll be a negative thing. So when we multiply A prime, when we multiply these two together to get A prime, we get a positive thing there and a negative thing there. That means that A is increasing and then decreasing. We've got a maximum by the first derivative test.